So the topic this evening is the Anthropocene. I'll explain what that is as we go along and its implication for our future climate. And I think it's probably, obvious to everybody in the room that we have unintentionally and unwittingly changed the planet, changed the climate of the planet, changed the biodiversity. And the question for us all is, can we, in a way, intentionally now engineer our planetary future so that for our grandchildren, for example, they will have as good a climate as we had in our time. I, as well as being from Scott Polar Research Institute, actually I live in Dorking and work from home. One of my tasks is to be a member of the Anthropocene working group. This is a group of people from around the world all working on different aspects of the Anthropocene. So moving forward then, I don't want to leave you with the view that this is all about doom and gloom, because it isn't. And what I'd recommend to you are these two books by a woman called Hannah Ritchie. Hannah is, I think, the assistant director of something called Our World in Data. You can Google Our World in Data and it will come up with all the sort of stuff that they do, but a lot of it is about climate change. And so here is that was 2025 book, this was 2023, not the end of the world. And you may not be able to read that from the back of the room, but it says how we can be the first generation to build a sustainable planet. So this is a very positive message. And in 2025, this year, she came out with this Clearing the Air, and I'll read that for you. A hopeful guide to solving climate change in 50 questions and answers. These two books are my Bibles. They help me to understand what's going on with our climate system, and they will help you too, and hopefully dispel the myth that we're all facing disaster and catastrophe. So moving on then, basic Anthropocene reading for any of you who really want to follow this up further. I know there's a book on the table at the back there about the Anthropocene as well. This one was written by a historian called John McNeill, and it's called The Great Acceleration. You'll see why in a moment, but it's an environmental history of the Anthropocene since he used 1945 as the, and then in 2019, my colleagues and I on the Anthropocene Working Group put together this thing. It's the Cambridge University Press book, The Anthropocene as a Geological Time Unit, a guide to the scientific evidence and current debate. And the principal editors were Jan Zelasevic, Colin Waters and Mark Williams, all from Leicester University and me. And there was a great constellation of actual writers and scientists producing the individual chapters. So the Anthropocene then, here it is. We humans, press the wrong button there. The Anthropocene, we humans have become a geological force on the face of the planet, basically. And we are in the process creating a new geological epoch. This is what the Anthropocene is all about. It is designed to be, to recognize that we are in a new geological epoch. So there are many geological deposits forming now, including a fingerprint that's distinct from that of the current Holocene epoch, with a lot of potential to remain in the geological record. So we're looking at the beginning of an epoch. And now this change that we're talking about is not the first detectable anthropogenic change. That could go back 30,000 years or even 100,000 years. This is not what we're interested in. What we're interested in is what has the great burgeoning of human civilization to give us a current population of 8 billion. What is that doing to the planet? We're not really interested in things that happened a long, long time ago when there were only a few people on the planet. So our view is that the Earth has experienced basically a rupture in its functioning. And we all know that our human well-being around the planet has grown significantly, but the planet in the process has become warmer and has become more polluted and less biodiverse. So the key question is, can we work to maintain our life support system? Now, if you talk to Hannah, she would say, well, yes, if we do the right things. So I can move this forward here. So let's look at this is the present ratified scheme. So here you see the Pleistocene and the Holocene. The Holocene began 11,700 years ago, and quite recently it's been divided into three, an upper, middle, and lower, with these fancy names over here, which we needn't concern ourselves with. Now, when geologists create a new geological unit, what they do is they mark its base with a golden spike. So these are not meant to be drawing pins, they are meant to be gold spikes that somebody hammers in at the base of what we've chosen. And that's done at the place where we have what we call a GSSP, which stands for a Global Boundary Stratotype Section and Point. So there are various places around the world where you would find the golden spike for the Meghallian, the North Grippian, the Greenlandian, all different places, of course. So now here we have the Anthropocene added on top of this as a stage 8. And what we wanted to do, having identified where we thought it started, which is mid-20th century, we put the case for there being a golden spike, meaning a global boundary stratotype section point for the base of the Anthropocene. This is how you play the game. Okay, so where do we go next? Well, our case was rejected at the end of 2023 by this body, the SQS, which is the Subcommission on Quaternary Stratigraphy. That's a bunch of elderly stratigraphers from around the world who meet in this subcommission, which is part of the IUGS, which stands for the International Union of Geological Sciences. Okay, and so we presented them with all of this evidence here. These are the places where our research teams around the world had identified spots where there was a very distinctive boundary dated to the middle of the 20th century. And what we had to do was to decide which one of these was going to be the type section for, sorry, yeah, I should get out of your way, which was going to be the place for the golden spike. And we chose this one, Crawford Lake in Canada, up here. And all of these other ones we had to present as secondary supporting evidence for this boundary. So it was rejected without any significant discussion, and we never got a report back from the subcommission as to why it had been rejected, except for a sort of throwaway remark, which was, well, there wasn't really enough geology in there, and it's too young to be geology, really. So we think, well, bugger you then. We're going to carry on working. So the Anthropocene Working Group still exists. Here we are. And so does the Anthropocene term. It's very widely used around the world, not only by geologists, but also by other science disciplines. So we humans are very successful. And this is an explanation of the great acceleration, which I showed you a book about early on. And what we see here is that socioeconomic trends accelerated after 1950. This is all of these graphs have 1750 on the left and 2010 on the right, and the dashed line down the middle there is 1950. So what you can see is that the way in which trends like population or GDP, how they really shot up after 1950. So 1950 was kind of a sort of singularity that separated everything that went before from everything that went after. So we see primary energy use, fertilizer consumption, water use, large dams, all of these kinds of things. And the reason was these were all the byproduct of more efficient industrial processes that were developed in World War II to make Spitfires, destroyers, tanks, bullets, and what have you, so that we could win the war. And at the end of World War II, they weren't needed anymore, not in the same volumes at any rate. And so these efficient industrial processes were diverted to satisfy growing consumer needs. Now, you know as well as I do that these trends aren't going to go on forever. They may have been rising since 1950, but the picture is that the rise is probably at some point going to be followed by a flattening out or by a decline. Could be a steep decline. We just don't know. Nobody is in a position to really tell us quite what's going to go on. But what we do know is that all of those activities have actually helped to damage our life support system. And these, oops, sorry, wrong one again. These these Earth system trends that you see here are also accelerated after 1950. So there's carbon dioxide in the atmosphere, accelerating after nitrous oxide, methane gas in the atmosphere. This one is actually inverted. This is stratigraphic ozone, which decreased. So that's a decrease that way. Surface temperature has increased. Ocean acidification has increased over here. Marine fish capture. Now you see the way that flattened out. That's because we got so good at catching fish that we couldn't really get any more. So canny people who wanted to keep selling fish started to develop aquaculture in a big way. There's an example there. Shrimp aquaculture has increased enormously since 1950. This one's an interesting one. Nitrogen supply to the coastal zone. If you're a farmer, am I treading on you now? I'm doing well here. I should stand between you two lads. Okay, so yes, nitrogen. So you're a farmer. What do? You want your stuff to grow, so you put nitrogenous and phosphate fertilizer on the fields, and when it rains, what happens? It washes off into the streams and into the rivers, and when it gets to the coast, we have a problem because algae love nitrates and phosphates, and so they grow like crazy, and then they die. And when they die, their bodies decompose, and that uses up oxygen. So what you end up with off big rivers like the Mississippi or in enclosed seas like the Baltic is you end up with a water mass that has almost no oxygen in it, and so you don't have any more fish. They're dead zones. So we have these nitrogen-created dead zones. Once again, you can see that this is the sort of prognosis. We have no idea where we're going to end up in the future, but we are sure that it's not going to go on increasing by huge amounts. So let's look at the main greenhouse gas that comes from burning fossil fuels. So at the top left here, we've got billions of tons of carbon dioxide emitted by fuel or industry. Okay, so here is going back to 1750. This is coal. So coal consumption increased quite steadily over a long period. And from 1950 onwards, you see that really began to increase quite fast. This is oil, not much oil being used prior to 1950, and then you can see the way that after 1950 that really shot up to be almost getting close to the amount of coal that's being burnt. And then we have in green, we have natural gas, and then these funny little things at the top. These are oddities. You've all probably seen pictures of flaring on gas fields. Okay, that produces CO2. But the other one is cement. When if you start with geology, okay, limestone is calcium carbonate. So what you do is you burn calcium carbonate, and it throws off the carbon dioxide and leaves you with calcium oxide, which is the grey stuff that you probably have used with sand and water to make cement in your backyard. So that's a tiny bit there. I keep doing that, don't I? Okay, so let's look at what were the annual carbon dioxide emissions from fossil fuels and also from land use. So here in blue is the actual measured outputs of fossil fuels, fossil fuel burning. And this in green is land use change. Now, land use change means developing fields, chopping down forests. Trees eat carbon. So if you're chopping all the trees down, you're going to get more carbon dioxide in the atmosphere. And what you have to do to get the whole picture is you add the land use change to the fossil fuels, and you get that red line, which runs up here and gives you about 40 billion tons of carbon dioxide in the atmosphere. So we can measure it in the atmosphere, and here it is. This is from January 15th, 1979, right up to the present time, well, late 2024. These are in parts per million, so this is 320 going up to 420. And so currently we are here at just over 420 parts per million of carbon dioxide in the atmosphere. However, there are other gases that we put into the atmosphere, like methane and nitrous oxide, which are also greenhouse gases. And so the way to assess the whole human impact is to do a conversion. You can convert the methane concentration and the nitrous oxide concentration to a carbon dioxide equivalent. And when you do that and you add that to the carbon dioxide, then the actual amount of our emitted greenhouse gases is not 420, it's 530. Not a lot of people know that, but this is one of the reasons why there is significant warming of the atmosphere. Okay, but not all, it's not all due, our warming is not all due to carbon dioxide emissions. Water vapor is the major greenhouse gas, but its role is limited by two things. First of all, when you get up into the stratosphere, it's so cold that the water just freezes out, so you don't get any water vapor in the stratosphere. And similarly, if I press this further, there we are. This shows you where water vapor is most concentrated in the atmosphere. So very concentrated in the tropics on both, here you see, and declining as we go further north and further south. And that's because when you get to the polar regions, it's so cold that all the water vapor freezes out. And so we know where water vapor is actually most important. So let's actually look at a graph and see what's happening. Where is global temperature going? So what you're seeing here is a graph from Jim Hansen, who used to be the director of NASA's Goddard Institute for Space Science. And so we start here at the left in 1880 and go right up to the present. 2025 is over here. And so the little black dots are the annual averages, and they are all joined by the blue lines. And then to make it easy to understand, the red line is the average that runs through all this. I'm going to change this to my own red pencil thing, because this one seems to be sort of fading off a bit. Right, so just a short technical pause here. Switch on and press the button. Yes, okay. So what we're looking at then is the way in which the average has changed with time. So it was pretty flat here. So the way in which one tries to understand these changes is by making them all relative to what the temperatures were in 1880 to 1920. So that's the average. So this zero line is the average for 1880 to 1920. And so all these values are anomalous values relative to that baseline. And so what we see is there has been this sort of increase with time. Now, I was intrigued by the slope of this line, so I put my ruler on there. So this green line is my ruler line, and I projected that into the future to see where it was going to go. What we see is that while the data was following the green line up to about here, it then started to diverge. This was 2016, and then there was a sort of decline, and then 2023 was up here, 2024 was up there, and 2025 is, for the current data that we have for 2025, is actually in between those two. And it looks very much as if we are now on a warming trajectory that's running up in this direction here. Now, the group that in the United Nations that's most concerned about this is something called the UN Framework Convention on Climate Change, which our government signs up to. And they meet every year in something called the Conference of the Parties. And you will probably be aware this week there is a Conference of the Parties number 30 meeting in Belém in Brazil. Okay, and what they have decided is that really we ought to try, if we can, to limit this warming from what it was in 1900 to 1.5. This would be the line for 1.5. And as you can see, we're already there. And they would like the maximum temperature, global average temperature, to be no more than 2 degrees. Okay, so where's the 2 degree line? 2 degree line is here. Okay. Well, it looks very much on this accelerated path as if we're going to get to 2 degrees of warming by about 2050, okay? And 2 degrees is quite a significant amount of warming. One of the reasons it's so significant is that in the polar regions, the amount of warming is between 2 times and 4 times the global average. So if they tell you that the temperature, global average temperature is going to be 2 degrees at some point in the future, that means in the Arctic it's going to be 4 or 8. Where's the ice in the Arctic? Antarctica, very similar. This is a recipe for disastrous melting, okay? So what else did I want to show you? Yes, there's a lot of natural variability wiggling around, but it doesn't take the averages much away from the sort of standard average curve. These peaks here are El Nino events. You all know what El Nino events are, I'm sure. Warm periods in the Pacific, and they are always followed by cool periods. The Peruvians called these El Ninos because they occurred at Christmas. So it's the boy child. And the following ones, which were the cold periods immediately afterwards here and down here, you see, were called La Ninas, the girl child. Okay, so there's another variation on here which affects things, and that is very large volcanoes, like Mount Pinatubo went off in 1991. And that put a huge amount of dust up into the atmosphere, which spread around the globe and acted like a giant umbrella, reflecting solar energy. And so what happened was the world cooled by about 0.2 of a degree for about 18 months, and then everything reverted to normal. Fortunately, we don't, at least within this whole time period, we don't get many of these very large eruptions. So governments are concerned about these changes. And one thing that they've sort of latched onto is the idea of what they call net zero. You may have seen net zero referred to in the press. Some of our politicians love it, some of them hate it. But what it means is you take out what you put in. So in other words, you can carry on producing fossil fuels, but you must, if they go from here to there, you must take out an equivalent amount so that the net CO2 remains flat. That's what net zero means. But there's one problem with this. It does not mean zero emissions. You can carry on with your emissions as much as you like, as long as you're pulling out the same amount that you put in. And the problem with that is that it maintains abundant carbon dioxide in the atmosphere, and that will maintain warming, melt ice, and keep the planet warm and sea level high. So these are the kinds of conundrums that we're currently faced with within the Anthropocene. We want to know, where's the Anthropocene going? What's likely to happen as we go further into the future? So let's have a look at that. Let's have a look at this. I often come across people who say, well, come on, Colin, the heat comes from the sun. It's got to be the sun. It's not our emissions. So let's look at the sun then. This goes from 1850 right up to 2025. And what we see is these ups and downs in the sunspots. Now, when you get large numbers of sunspots, we get more solar energy arriving on Earth. Okay, so you'd sort of expect that to have some effect on the temperature. Well, here's the temperature graph. That's a variant of the one we just saw. And you can see that there's no significant relationship at all between what's actually happening to the global temperature and what the sun is doing. And that's because the solar energy bursts here are actually rather weak. We can measure them, but they are actually rather weak. So there's another piece of information hidden here, shown by my red circles. This highlights the fact that in 1860 and 1870, there were quite a lot of sunspots, but they were the same number of sunspots as we had in 1980 and 1990. So strictly speaking, if the sun was responsible, then the temperatures in 1980 and 1990 should have been the same as they were in 1860 and 1870. Okay, here's 1980 to 1990, and here is 1860 to 1870. No comparison. There's another interesting feature here, and that is that we see in this graph, you see this sort of flattening going on here. And this is that period after this 1950 is right around in here. And so you see that the curve was rising up slowly and then it flattened out. This is because that's when the great acceleration began with all those new industrial mechanisms for creating consumer goods after the Second World War. And this was a really dirty process. Some of you in this room, including me, might have been old enough to experience the London smog of 1952 to 1953. I mean, I could walk down the street and not see my hand in front of my face. And it killed something like 3,000 people in London. So these were pretty dire events. And the government was mighty worried about that. And so in 1954, we had the first, in the UK, the first Clean Air Act to try and clean up all this mess. And those Clean Air Acts started getting more and more stringent until about 1976. The last one was, I think, in the UK. And once we cleaned the air up, you can see that the global warming signal was able to emerge from being hidden behind that cloud of industrial crap in the atmosphere. And this was true around the world, and many countries followed the UK's lead in developing Clean Air Acts. And that net result is, that's why the curve looks the way it did. Okay, so there's another piece of evidence that we can use to show just how unnatural what we have now is. And on the right, you're looking at the hand of somebody in a glove from the British Antarctic Survey. Now, at the British Antarctic Survey, they store solid rods of ice that we've drilled down through the Antarctic ice sheet, and it really is that thick. And those rods are recovered by the drill bit in lengths of about 1 meter, and then they're taken away to stores. One of the stores is in Cambridge at the British Antarctic Survey. And what they've done there is they've taken a slice off the top of one of these, and they're shining a light through it. And what you can see is all these things that look like little nodules. These are actually bubbles of trapped air, fossil air. Who would ever have thought as a geologist that you could find fossil air? Well, there it is. You know, what do you hear when you walk on snow? Crunch? Okay. Any idea why that is? What's happening? Yes, it's the air coming out. It's the crystals being banged together, but it's also the air coming out. Because when snow falls, it falls usually very, very slowly and traps quite large pockets of air. So in a recent snowfall, a lot of it is just air. And then as more and more snow came down and more snow came down, the weight of it eventually would compress those pockets until by the time you get down to the level where the snow actually forms into ice, what you have instead of a pocket is a bubble. And so we can put this piece of ice in a beaker, in a closed beaker, and heat it up and get the air out and analyze it for its carbon dioxide concentration. So this is what's been done here. These are different symbols here represent lots of different ice cores from different parts of Antarctica. They all tell the same story that this is the year 2000, this is the year 1000. So for most of the past 1,000 years, the air in Antarctica carried 280 parts per million of carbon dioxide. Okay? Now that line, the vertical line there is 1769, and what you see is from there, the CO2 in these ice cores starts to increase, and it increases faster and faster and faster, and eventually it matches on to the blue line, which is what we've been measuring in air. Not any old air, not near industry, but in background air in nice, quiet places around the world, like South Pole, top of Mauna Loa volcano, where it's just westerly winds across the Pacific. So that's what the CO2 looks like. Now, this graph was produced in 2009 by David Mackay. And so the top here didn't get up to the top of the graph, which was 400 parts per million. We're now at 427 parts per million. And so what this means is that we are increasing carbon dioxide in the air by 20 parts per million per decade. And the fastest that nature did it in the past 800,000 years of that ice core, the longest ice core, was 20 parts per million in 1,000 years. So we are doing this 100 times faster than nature. So it's not too surprising that we have a problem. And so there is a lot of different kinds of data around that help us to understand what's going on. This may surprise you because what it says is that 90% of the heat of global warming isn't in the atmosphere, it's actually in the ocean. And so to measure it, we use something called the ocean heat content, OHC over here. This is going from about 1955 all the way up to 2025. And the annual mean is the baseline from 1981 to 2010. So prior to about 1998, most of these values were below that baseline. And then since then, they've been really increasing faster than they were back down here, much like the temperature, the global average temperature that we saw. Okay, so now there is a surprise in this data. If we ceased our carbon dioxide emissions, the carbon dioxide that is also being sucked into the ocean and the heat in the ocean will emerge from the ocean until the balance between the oceanic and atmospheric amounts of heat and carbon dioxide are in balance, in equilibrium. Right now they're not. They're way out of equilibrium, which is why we've got a problem. So the future will be kind of interesting and different. So as a net result of warming, let's see what happens when you warm water. Anyone? Thank you. It expands. What happens if you melt ice on land? You get water. Okay, so the ocean gets a double whammy. It heats up, and so it expands, and it also gets the water from melting ice. So when we go back to 1995 to about 2003, what we see from the sea level, this is global sea level trends, is that they were running at about 2 millimeters per year. But after that, they started to diverge, and now they're running at 5 millimeters per year. I use my ruler again. I put my ruler through the data down here. And you can see by how much a considerable amount the sea level is now diverging. Now, what's interesting is the fact that the sea level rise lags the temperature and lags the carbon dioxide. And there's a really simple reason for that. If you heat ice in the Arctic, it may start out at -30. And in order to get it to melt, you've got to get it to 0. And it takes quite a long time to get ice up to 0, at which point it will actually melt. So if we stabilize carbon dioxide through net zero, the sea level will go on rising because it's lagged from the carbon dioxide rise. Okay. And just to give you an example of that in the real world, we're going back 20,000 years here, and that's actually projecting into the future, but 0 is today, okay? So when we go back in time, this is the last glacial maximum 20,000 years ago, and there's the sea level. It was about -130 meters, and as the Milankovitch orbital frequencies changed, giving us more heat, the temperatures rose, and so did the sea level. Now, eventually, the orbital forcing through Milankovitch cycles stopped at 11,700 years ago, which is now the beginning of the Holocene. And the temperature stopped rising, and the carbon dioxide coming out of the ocean also stopped rising. But the sea level kept going for another 45 meters until 7,000 years ago. All of this rise here in sea level was due to the melting of the great North American and Scandinavian ice sheets. It takes a long time to melt an ice sheet. And so this is an example of the really considerable lags that we can expect in the rise in sea level. And from then on, sea level was more or less stable. And the question for us all in the Anthropocenes, if we start and call 0 1950, where are we going to go? Well, you can say, well, it depends on how much carbon gets put into the atmosphere after the year 2000. If it was a smallish amount, we might get that much rise. Reading across the scale here, so that could be about 10 meters. If we put rather more in, then we could get up with about 20 meters, and so on. So modern sea level is already lagging the warming, and that will continue just as it did in the past. Right, so ice is very important, not just because if it melts, it's going to rise sea level, but because it's highly reflective. White snow and white ice, they reflect solar energy back into space. So that gives us a higher albedo. And if we lose that sea ice reflection, that warms the polar regions more. So the polar regions get this sort of double whammy effect. So what I want to do is to compare now the Arctic with the Antarctic. And the immediate difference is that the Arctic has an ocean surrounded by land, and the South Pole has land surrounded by ocean. So they are so geographically different, you should not expect them to behave in the same sort of way in response to global warming. So let's look at what's happening in the Arctic. The warm winds can get in, as shown by these white arrows, from almost anywhere. And you might, even from the back of the room, be able to see there are some red arrows bringing warm water in from the North Atlantic. So for two reasons, this means it's relatively easy to melt sea ice in the Arctic. It doesn't do anything to sea level, because sea ice is just the frozen surface of the sea. It freezes in winter, melts in the summer. It doesn't change sea level. So there's the sea ice melt in the Arctic starting in 1978 with satellite measurements. And you can see this is for October at the end of the summer. So you can see some wiggling around, and then the losses get steeper. And you can see from the dashed line running through that's the sort of trend for the sea ice melting. So in the Arctic, they've already lost half of their sea ice, their reflective sea ice, and the sea ice itself has changed. It used to be up to 5 meters thick. Now it's usually no more than 1 meter thick. So let's see what's happening in Antarctica. It's different, okay? You've got these very strong winds running around the continent. The continent is very high. It's a huge upstanding mass, gets up to 4,000 meters. And so the winds just run around it, and they push current, the Antarctic circumpolar current around here. And those two together act as a wall, keeping heat away from Antarctica very conveniently. So when we look at, we start 1978 again, when satellite measurements began, going up to 2025, and we see that there was some wiggling around here, and the wiggling's got a bit bigger. And then suddenly, around about 2015, the bottom dropped out of this, and we've been getting very low values in sea ice since then, very much lower than we started with back in 1978. So the sea ice is now also melting in Antarctica. And one of the reasons for that is that the Southern Ocean is getting warmer, and I'll explain how that works in a moment. Okay, but you can certainly see for yourselves there the huge difference between the two. So the land ice is equally important. So what we're looking at here is, this is a physiographic map of Antarctica showing height. So the red is higher than 3,000 meters. So this part of Antarctica, which we call East Antarctica, that's because this is the Greenwich Meridian due south of us. And so all of this part of Antarctica is very high. And all of this part of Antarctica, we call West Antarctica, is very much lower. It's these nice turquoise and dark blue colors. If all of the ice in the west part of Antarctica melted, the sea level would go up by about 55 meters. And that has, of course, happened in the past. In Cretaceous times, the reason we have so much chalk around here is because all of this area was flooded by the sea, which was full of plankton. And that's because there was no ice sheet at the time, not at all in late Cretaceous times. Let's look at Greenland. It's very similar looking. It does get up to more than 3,000 meters. That's the red area. And if all the ice here melted, it would raise sea level by 7 meters. If all of the ice in this West Antarctica melted, it would raise sea level by 5 meters. Now, we know from various experiments around the world and cores taken in the ocean and so on that the total amount of sea level rise during past warm periods was about 10 to 15 meters over a period of 300 to 500 years. And 10 to 15 meters really sort of represents the addition of Greenland melting with West Antarctic melting without much coming from East Antarctica. So let's see what's going on now. This is mass loss in gigatons. A gigaton is 1 billion tons. Got no idea how many African elephants that would be, but a lot. So let's see, this Greenland, this is 1992, going up to about the year 2000. Neither Greenland in blue or Antarctica in red were melting very fast. But from then on, from about 2002, you see Greenland really started to melt quite rapidly, and it's still melting quite rapidly, and it's lost almost 6,000 gigatons since 1992. Antarctica is melting less fast because of all that protection I just talked about, but it's still lost around about 2,500 gigatons. The one thing you do notice here is that this is a fairly steady loss, and then you get this lump at the end. That's about 100 extra gigatons. So there's a slight increase. That increase is due to that melting of the sea ice. If you melt the sea ice near to the continent, what you get are warm winds that take the moisture from that melt area over the land and dump it as snow, which actually gives rise to that little lump that you see just there. So all of these different things hang together very nicely. Switzerland, I noticed somebody here's got, yes, there you go. That's the Great Aletsch Glacier. And you can see that that's what it was in 1949, right the way down to here. I think this might have been used in a James Bond film, this thing here. And this is 2024, and the glacier only comes down now to just about here. So all of this area is now ice-free. And the Swiss have added together all of the information about their glaciers. And so from 1950, you see not a lot of change up until here, which is about 1980. And then suddenly it starts to get lost, and then the loss rate steepens as we get towards 2025. This is true of all mountain areas anywhere in the world. So we are losing ice, folks. The ocean is important too. What we can see here are pole-to-pole connections. We're very fortunate. This is from Greenland, right the way down to Antarctica, straight the way down through the Atlantic. And what we see is warm water being carried north from the Southern Ocean all the way up to the north. Here we know it as the Gulf Stream. As that water moves north, evaporation makes it saltier, and when it gets towards Greenland, it gets cold enough to actually sink and return back to the Southern Ocean. Similarly, some of this water goes back towards Antarctica. And here we meet sea ice again. When the surface of the sea freezes, the ice that forms is so fresh you could put it in your mouth and suck it, and you wouldn't get any salt in your mouth. The salt is excreted into the water below, and it makes that water brine-like and dense. So the water under the sea ice sinks right the way down to the seabed and goes all the way up to about the latitude of Portugal, and then it joins this circulation. So we call this circulation here the Atlantic Meridional Ocean Circulation, or AMOC for short. And what we are seeing is that this northern bit, the Gulf Stream bit, is beginning to slow down, and that's got some people worried. And if the whole thing slows down, it means that more heat stays in the South Atlantic and less heat gets towards Greenland. So the North Atlantic cools and the Southern Ocean warms. This is something to watch out for in the future. I'm going to skip over that one because it's too much detail. So some guys in Germany at the Potsdam Institute of Climate Change decided they wanted to see how future ice volume in the Anthropocene would change. Now, this is the current picture at the top. And what it shows is going from today on the left, that's 100,000 years. These are hundreds of thousands, 100, 200, 300, 400, 500,000 years. And so we see that the next ice age, this is maximum ice, would occur between 50 and 100,000 years into the future. And then there'd be another one and another one. This is exactly like the Pleistocene variation. So they're driven by the Earth's orbital variability. In the future, because of the amount of heating we've got and the carbon dioxide in the atmosphere, we expect, or they expect, that the next ice age would be postponed to almost 180,000 years into the future, that the ensuing glaciations would be reduced compared with what we now expect, and there would be other periods in the future when there would be zero ice, when the current projections suggest we should get a lot of it. So these are big changes that we expect in the Anthropocene if we don't do something about the greenhouse gases. I want to move this forward, and so I press that one. Yep. So there are always winners and losers, and what this shows you is the precipitation. By 2080 to 2099, the end of this century, dry areas will get drier and wet areas will tend to get wetter. So this is, we're heading for droughts versus floods. All of the brown areas are going to get very much drier. So the Mediterranean basin is going to be very, very dry. Southern United States, Central America, Chile, Brazil, Southern Africa, and southernmost Australia are going to be having problems. In the UK, right where we're sitting at the moment, you can perhaps see the southernmost UK has a little dash of yellow, so it'll be drier. And Scotland has a more darker blue. It'll get slightly wetter. I'm not sure why that's not going forward. Let's try it again. There we are. Okay. Now, we're always seeking for analogs for tomorrow, and this is the key one. This is the Pliocene, the middle Pliocene, 3 million years ago. The climate then was 3 to 4 degrees warmer. It was 10 degrees warmer at the poles, and sea level was up by 10 to 12 meters. And the amount of carbon dioxide in the atmosphere was about what it is today, between 4 and 450 parts per million. Now, the geologists working on Antarctica, even way back in 1991, recognized that at that time, the ice sheet had shrunk back to this area here, leaving ice on the mountain areas. These are transantarctic mountains, and on other small mountain areas like these ones over here. And all of the stuff that's white, which is now ice, would actually be ocean. So a very different looking Antarctica. And so we needed to find out just how realistic that was. So a consortium known as ANDRIL drilled just near McMurdo Station, just near Captain Scott's hut, around about here. And this is their core. It goes back into the Miocene times. In the Miocene, we see orange, which is due to the fact this Mount Erebus is right there. So it's a live volcano, and it erupts every now and then. And all of this green and gray stuff is actually glacial debris coming off these mountains and going into the Ross Sea. Then suddenly, in the mid-Pliocene, we start to see these things colored yellow. This is long periods in which the only sediment was Pliocene diatomeous. That means that the whole Ross Sea ice shelf had disappeared, and you had a marine incursion with plankton. And gradually, with time, as we go into the later Pliocene, you see glacial material starts to come back, but there are still some episodes of plankton. Not in recent times. In the Pleistocene, it's all glacial debris. So we have a good idea of what Antarctica is going to look like. So how are we doing, generally speaking? Well, we're doing pretty well with our renewable energy. Renewables overtook coal as the world's biggest source of electricity this year. So that's good news. And what else have we got here? Oh, come on, press the button. Yes, the future is coming. We're seeing massive electrification, and what you see here is the rise and rise of electric cars. So 2012, there were not many electric cars at all. These figures here are millions. That is 18 million over here. And so you can see the rise, a slow rise here to about 2019, and then wow, it really takes off. There it goes. And the brownish color is China. The bluish color is the European Union. The green is the laggard, which is the United States, and the gray areas are the rest of the world. And it turns out that the reason for this is that the more of these you make, the more of them you build, the cheaper they get. So more and more people want these things. So if I press that again, and here's another part of the future. This is coming, folks. It's already here. We're just waiting for it to develop faster. You probably saw this on telly in 2020. This was UK's first hydrogen-powered train, an experimental one. And then in Surrey, 2024, this is hydrogen-powered bus fleets have hit the streets. I mean, I followed one of these through Reigate the other day. Now, this bloke here, you all know about JCB diggers and JCB bulldozers. This is Mr. JCB, JC Bamford. And he was sure that the internal combustion engine could be changed to run on hydrogen. So he challenged his engineers to do that, and they did. So he's proudly holding here the first hydrogen engine for his huge vehicles that are on many of our building sites. So these things are happening all around us. And even planes. This is a Norwegian plane. It's a hybrid, so it's running on batteries and on aviation spirit. It's quite small, so it only takes about 8 passengers. This one's on its way to Stavanger in Norway. And so we're going to see more of those sorts of things as well. And the transition is already here. For example, everybody talks about lithium-ion batteries, right? Did you ever hear anybody talking about sodium-ion batteries? Well, sodium is next to lithium in the periodic table. And it turns out we have loads of sodium because all over Europe we have massive salt deposits. Europe was a major source of major area for salt mining. Here we have this. The company is called 11. It's a sodium battery because salt is abundant and cheap. And this is a battery system for storing electricity in your house. And there are rapid developments going on in the UK, Germany, USA, and so on and so on and so forth. So watch this space. We're going to see more of that kind of thing. But there are challenges also to biodiversity. It's not simply about climate change, or it's about climate change, but it's also about biodiversity. And this example shows that in some areas we have boreal forests that just love soaking up carbon dioxide. And so what we see is what some people call greening the planet, an expansion in the vegetation cover. But in other areas, this is in Canada, in the pine forest, the abundant heat means that some insects that normally would only breed twice a year are now breeding 3 times a year because it's warmer. And what are they doing? Eating the bark off all the trees and killing them off. So this might be greening the planet. This is browning the planet. And so those are other things that we need to watch for in terms of the kind of things we're going to see. So we're looking at a major perturbation caused largely by our activities, and we think that this major perturbation does justify naming the Anthropocene as terminating the Holocene epoch. Greenhouse gases are trapping too much energy, we are overheating. If we achieve net zero, which governments seem to be fond of, then what it would lead to immediately are high temperatures that would persist for a long time. I don't think most politicians know that. Population is often cited as something that's driving emissions, but it's not true. Population and emissions are not directly connected. It's the wealthy people on the planet that are actually creating most of these emissions. I mean, you take any poor country around the world and they represent something like at least half of the 8 billion people on the planet live in very poor countries. Their carbon dioxide contribution is next to nothing. So most of the carbon dioxide that we see comes from wealthy areas. The levels of the warmth that are likely by the end of this century, we have not seen them since the early late Pliocene 3 million years ago. The warm interglacial conditions, we think, are likely to persist for at least 50,000 years, but probably longer under our CO2 emissions. And finally, the continued warming will reconfigure the biosphere, just like I showed you. And we believe this all justifies the naming of a new epoch. So where do we go from here? Yes, this is about choices. Now, you're all people. Many of you have grandchildren. What would you like to have as a climate for your grandchildren? Because this is part of what the choices are about. We were here in the Holocene. We were there by 2016 on our way up. And if we wanted to keep the temperature rise globally to less than 2 degrees and the sea level rise to less than 2 meters, then we need to quit what we're doing and stick somewhere around about here for our Anthropocene climate. If we carry on with business as usual, we'll run straight past where we were in 2016. We'll end up somewhere here where the temperature rise globally will be between 3 and 5 degrees, and the sea level rise will be somewhat more than 10 meters. Now, just for your information, from the latest Conference of the Parties meeting in Belém, the forecast is that the temperature rise by 2050 will be 2.8 degrees centigrade, which is very close to 3 degrees centigrade. So I'll leave you, I think, with that thought. The end. And where are my penguins? Somewhere in here. Yes.
Very good.